In particle physics, every type of particle of ordinary matter, as opposed to antimatter, is associated with an antiparticle with the same mass, but with opposite physical charges, such as electric charge. For example, the antiparticle of the electron is the positron, also known as an antielectron. While the electron has a negative electric charge, the positron has a positive electric charge and is produced naturally in certain types of radioactive decay. The opposite is also true. The antiparticle of the positron is the electron. Some particles, such as the photon, are their own antiparticle. Otherwise, for each pair of antiparticle partners, one is designated as the normal particle, the one that occurs in matter usually interacted with in daily life. The other, usually given the prefix anti-dash, is designated the antiparticle. Particle-antiparticle pairs can annihilate each other, producing photons. Since the charges of the particle and antiparticle are opposite, total charge is conserved. For example, the positrons produced in natural radioactive decay quickly annihilate themselves with electrons, producing pairs of gamma rays, a process exploited in positron emission tomography. The laws of nature are very nearly symmetrical with respect to particles and antiparticles. For example, an antiproton and a positron can form an antihydrogen atom, which is believed to have the same properties as a hydrogen atom. This leads to the question of why the formation of matter after the Big Bang resulted in a universe consisting almost entirely of matter, rather than being a half-and-half mixture of matter and antimatter. The discovery of charge parity violation helped to shed light on this problem by showing that this symmetry, originally thought to be perfect, was only approximate. The question about how the formation of matter after the Big Bang resulted in a universe consisting almost entirely of matter remains an unanswered one, and explanations so far are not truly satisfactory overall. Because charge is conserved, it is not possible to create an antiparticle without either destroying another particle of the same charge, as is for instance the case when antiparticles are produced naturally via beta decay, or the collision of cosmic rays with Earth's atmosphere, or by the simultaneous creation of both a particle and its antiparticle, pair production, which can occur in particle accelerators such as the Large Hadron Collider at CERN. Particles and their antiparticles have equal and opposite charges, so that an uncharged particle also gives rise to an uncharged antiparticle. In many cases, the antiparticle and the particle coincide. Pairs of photons, Z0 bosons, pi0 mesons, and hypothetical gravitons, and some hypothetical WIMPs all self-annihilate. However, electrically neutral particles need not be identical to their antiparticles. For example, the neutron and antineutron are distinct. History experiment in 1932, soon after the prediction of positrons by Paul Dirac, Carl D. Anderson found that cosmic ray collisions produced these particles in a cloud chamber, a particle detector in which moving electrons, or positrons, leave behind trails as they move through the gas. The electric charge-to-mass ratio of a particle can be measured by observing the radius of curling of its cloud chamber track in a magnetic field. Positrons, because of the direction that their paths curled, were at first mistaken for electrons traveling in the opposite direction. Positron paths in a cloud chamber trace the same helical path as an electron, but rotate in the opposite direction with respect to the magnetic field direction due to their having the same magnitude of charge-to-mass ratio, but with opposite charge and, therefore, opposite sign charge-to-mass ratios. The antiproton and antineutron were found by Emilio Segre and Owen Chamberlain in 1955 at the University of California, Berkeley. Since then, the antiparticles of many other subatomic particles have been created in particle accelerator experiments. In recent years, complete atoms of antimatter have been assembled out of antiprotons and positrons, collected in electromagnetic traps. Dirac hole theory solutions of the Dirac equation contain negative energy quantum states. As a result, an electron could always radiate energy and fall into a negative energy state. Even worse, it could keep radiating infinite amounts of energy because there were infinitely many negative energy states available. To prevent this unphysical situation from happening, Dirac proposed that a sea of negative energy electrons fills the universe, already occupying all of the lower energy states, so that, due to the Pauli exclusion principle, no other electron could fall into them. Sometimes, however, one of these negative energy particles could be lifted out of this Dirac sea to become a positive energy particle. But when lifted out, it would leave behind a hole in the sea that would act exactly like a positive energy electron with a reverse charge. These holes were interpreted as negative energy electrons by Paul Dirac and mistakenly identified with protons in his 1930 paper, A Theory of Electrons and Protons. However, these negative energy electrons turn out to be positrons and not protons. This picture implied an infinite negative charge for the universe, a problem of which Dirac was aware. Dirac tried to argue that we would perceive this as the normal state of zero charge. Another difficulty was the difference in masses of the electron and the proton. Dirac tried to argue that this was due to the electromagnetic interactions with the sea, until Hermann Weyl proved that hole theory was completely symmetric between negative and positive charges. Dirac also predicted a reaction E minus plus P plus gamma, where an electron and a proton annihilate to give two photons. Robert Oppenheimer and Igor Tamm, however, proved that this would cause ordinary matter to disappear too fast. A year later, in 1931, Dirac modified his theory and postulated the positron, a new particle of the same mass as the electron. The discovery of this particle the next year removed the last two objections to his theory. Within Dirac's theory, the problem of infinite charge of the universe remains. Some bosons also have antiparticles, but since bosons do not obey the Pauli exclusion principle, only fermions do, hole theory does not work for them. A unified interpretation of antiparticles is now available in quantum field theory, which solves both these problems by describing antimatter as negative energy states of the same underlying matter field, i.e., particles moving backwards in time. Elementary antiparticles composite antiparticles particle. Antiparticle annihilation: if a particle and antiparticle are in the appropriate quantum states, then they can annihilate each other and produce other particles. Reactions such as E minus plus E plus gamma gamma, the two-photon annihilation of an electron-positron pair, are an example. The single-photon annihilation of an electron-positron pair, E minus plus E plus gamma, cannot occur in free space because it is impossible to conserve energy and momentum together in this process. However, in the Coulomb field of a nucleus, the translational invariance is broken and single-photon annihilation may occur. The reverse reaction, in free space, without an atomic nucleus, is also impossible for this reason. In quantum field theory, this process is allowed only as an intermediate quantum state for time short enough that the violation of energy conservation can be accommodated by the uncertainty principle. This opens the way for virtual pair production or annihilation, in which a one-particle quantum state may fluctuate into a two-particle state and back. These processes are important in the vacuum state and renormalization of a quantum field theory. It also opens the way for neutral particle mixing through processes, such as the one pictured here, which is a complicated example of mass renormalization. Properties quantum states of a particle and an antiparticle are interchanged by the combined application of charge conjugation C, parity P, and time reversal T. C and P are linear, unitary operators. T is antilinear and anti-unitary. Psi T phi equals phi T minus 1 psi. If P, sigma, and denotes the quantum state of a particle n with momentum p and spin j, whose component in the z direction is sigma, then one has CPTP, sigma, n equals minus 1, j minus sigma p, minus sigma, nc, where nc denotes the charge conjugate state, that is, the antiparticle. In particular, a massive particle and its antiparticle transform under the same irreducible representation of the Poincare group, which means the antiparticle has the same mass and the same spin. If C, P, and T can be defined separately on the particles and antiparticles, then Tp, sigma, n is proportional to minus P, minus sigma, n, CPP, sigma, n is proportional to minus P, sigma, nc, Cp, sigma, n is proportional to P, sigma, nc, where the proportionality sign indicates that there might be a phase on the right-hand side. As CPT anticommutes with the charges, CPTQ equals minus QCPT. Particle and antiparticle have opposite electric charges Q and Q. Quantum field theory. This section draws upon the ideas, language, and notation of canonical quantization of a quantum field theory. One may try to quantize an electron field without mixing the annihilation and creation operators by writing psi x equals sigma kuk x, ak e minus I e k t, where we use the symbol k to denote the quantum numbers p and sigma of the previous section and the sign of the energy e k, and ak denotes the corresponding annihilation operators. Of course, since we are dealing with fermions, we have to have the operators satisfy canonical anti-commutation relations. However, if one now writes down the Hamiltonian H equals sigma k k ak, then one sees immediately that the expectation value of H need not be positive. This is because EK can have any sign whatsoever, and the combination of creation and annihilation operators has expectation value 1 or 0. So one has to introduce the charge conjugate antiparticle field, with its own creation and annihilation operators satisfying the relations Bk equals AK and dB, K equals AK, where K has the same P and opposite sigma and sign of the energy. Then one can rewrite the field in the form psi x equals sigma k plus uk x, ak e minus I e k, t plus sigma k minus uk x, bk e minus I e k t, where the first sum is over positive energy states and the second over those of negative energy. The energy becomes H equals sigma K plus EK AK plus sigma K minus EK BK plus E0, where E0 is an infinite negative constant. The vacuum state is defined as the state with no particle or antiparticle, i.e., AK0 equals 0 and BK0 equals 0. Then the energy of the vacuum is exactly E0. Since all energies are measured relative to the vacuum, H is positive definite. Analysis of the properties of AK and BK shows that one is the annihilation operator for particles and the other for antiparticles. This is the case of fermion. This approach is due to Vladimir Fock, Wendell Furry, and Robert Oppenheimer. If one quantizes a real scalar field, then one finds that there is only one kind of annihilation operator. Therefore, real scalar fields describe neutral bosons. Since complex scalar fields admit two different kinds of annihilation operators, which are related by conjugation, such fields describe charged bosons. Feynman, Stuckelberg interpretation by considering the propagation of the negative energy modes of the electron field backward in time, Ernst Stuckelberg reached a pictorial understanding of the fact that the particle and antiparticle have equal mass m and spin j, but opposite charges q. This allowed him to rewrite perturbation theory precisely in the form of diagrams. Richard Feynman later gave an independent, systematic derivation of these diagrams from a particle formalism, and they are now called Feynman diagrams. Each line of a diagram represents a particle propagating either backward or forward in time. In Feynman diagrams, antiparticles are shown traveling backwards in time relative to normal matter, and vice versa. This technique is the most widespread method of computing amplitudes in quantum field theory today. Since this picture was first developed by Stuckelberg and acquired its modern form in Feynman's work, it is called the Feynman-Stuckelberg interpretation of antiparticles to honor both scientists.